Hello, this tutorial covers Leckwall's beam spring method of analysis for partially composite insulated wall panels. What do we mean by partially composite? Well, you can see from the stress diagram the difference between a non-composite panel and fully composite. And partially composite is kind of in between. You can see the actual behavior versus the percent composite assumption that Leckwall has traditionally used. Uh, and so with the new beam spring model, we are trying to model the actual behavior versus a percent composite assumption. Uh, Here are some typical partially composite connectors that you may have seen. And in order to find uh, the, uh, the characteristics of these connectors, they've been tested in a double shear setup. And using that, we come up with a strain diagram. We have two regions. You have the elastic region here and in the inelastic region where there is no coming back from the inelastic. So we want to stay in the elastic region. Leckwall assumes that the connectors stay elastic at all times, even for ultimate loads. This provides a factor of safety for service loads and ensures that the connectors will always remain elastic. So there are basically four values that we need: the elastic limit force and the ultimate limit force, and its corresponding uh, connector slip or deformation. And we take those values and use them uh, as the input for a frame analysis, a Vierendeel truss type analysis, where uh, these springs represent the connectors and they have shear deformations, which correspond to that graph you just saw. The blue lines are the concrete withes, the withe elements. So let's get started. Okay, this file is mild reinforced with a few openings. I've pre-filled it to save time. Uh, so from a previous tutorial, you know that we can go to the wizard and go through these steps one by one for uh, this analysis. First thing to note is we have three different methods of composite calculation. The manual percent composite is something longtime users would be familiar with. You have percent composite for stresses, ultimate, and deflection. Uh, these other two methods are newer. The ISBT stands for iterative sandwich beam theory. It's an older method, a precursor, and it's a simpler method. You can see from the note here that the beam spring method is preferred. That is because it's more accurative than the elastic iterative. Okay, the ISBT method is included to maintain compatibility with earlier versions. So the panel is 333, 3-inch insulation, 330 inches long, standard properties, mild reinforcing input. We need to input the mild reinforcing and openings before we can specify the connectors. So you can see the openings have already been entered. Here is the connector screen. You can see using 10 rows across, with a generic connector with the following properties. There's often an advantage to adding extra connectors in the end rows, and the software lets you do that. Also, for certain manufacturers, you could specify a primary connector and also a secondary connector at the ends. The secondary connectors can perform similar to adding additional connectors in the first, second, or third rows, and it adds ultimate capacity. You can see we've got 53.8%. If I add additional connectors, and check again, we're up to 64.7% in this case. Additionally, you can add solid zones at the top and bottom. The program will tell you how much solid zone you need to provide full composite action for ultimate strength. Here we're showing 36.8 inches at the top of panel and 58.5 required from the bottom because we have a door opening. Enter reveals. Nothing new here. We are going to skip handling, but just so you know there, if you check this box, it will use the beam spring method to calculate the partial composite properties for stresses and ultimate. Okay, panel supports. We have a small parapet at the top, 12 inches down from the top. Otherwise, nothing special. Main structural width is on the inside, which is the top width usually. Here with the beam spring method, we can select the bearing either on the inside width, outside width, or both widths. Typically, you would support it on both widths with the shims spanning across. Also, some special options if you have a cantilevered base, such as a retaining wall or a hung panel, where the panel is hung from a frame and does not rest on the foundation. Wind load, earth pressure, nothing new there. Okay, for concentrated loads, now with beam spring, we can select the bearing width for each concentrated load. Usually, if you have a haunch on the inside of a panel, it's going to bear on the inner width only, as is shown here. Sometimes you may have a connection such as a tube haunch, which penetrates both widths and is anchored in both widths, in which case you would select both outer and inner for your bearing. Okay, so half-inch bow, admin height, 25-degree temperature differential. All right, so we have beam spring method selected. We selected that in the section dimensions screen. So first thing I usually do is find the worst load case for tension stress. And here looks like load cases 4 and 6 are the critical load cases. You can see here the panels are cracked. That doesn't mean the panel has failed because these are ultimate strengths. If you check service load case, the panel isn't cracked, but the service tension is exceeded if you were trying to control cracking. We can find, let's go back to load case 4. We can find more information about the beam spring analysis here. Here's our plan for load case 4. This is telling us the connection slip that we're getting. 0.0429 is the, or 0.0477 is the maximum, less than 0.05. So we know that our connectors are in the elastic limit for ultimate loads. Again, this gives you the shear in the connector. It's not the shear per connector, but per a 3.3 inch segment of length by the full panel width. Horizontal shear is useful when you have solid zones to make sure your solid zones do not exceed the ASTI limit of 60 psi. This diagram is showing us how much composite action for stress the connectors are giving us. You can see that it varies along the span, so it's not a consistent number. That's why we need the analysis to tell us exactly what we're getting. Okay, we're ready to check the interaction curves. All right, so this is familiar to most, the ultimate percent composite check. Here, the beam spring is telling us we have 54% composite at the midspan. Our critical location is just below the window. We can use the arrow keys to move this slider over. And it shows that we're still okay. A new feature with beam spring is the ability to check the outer and inner withes independently, separately. This is more accurate than going with the percent composite analogy. So the outer withe for suction is going to be in tension, for pressure is going to be in compression. We can do our auto check again, and we can see the critical location is around the same place. We're okay, but it's getting closer. We can do the same thing with the inner withe. And we've got similar results. Another option to check is the axial tension. If we have a crack section, so let me quickly go back to here. We have selected that the member is pre-cracked. Actually, the program has selected it. If you have a mild reinforced slender panel with gravity loads, the program assumes you want to do a pre-cracked analysis. This is commonly used in tilt-up construction. You can see a reference to an ACI tech note regarding this. It assumes the panel is fully cracked and magnifies the P delta or secondary moment deflections to account for that. So when you do that with an interaction curve and you're checking the individual Y's, here you have M sub U, say up to 66.8 kip inches. Now, that is assuming uncracked. Now we want to see what happens when these Y's are cracked. And when we do that with a withe axial tension check, your actual moment goes way down because your Y's are a lot less stiff. They can't carry as much, and the connectors are carrying much more of the force. And here you see our connector tension is, or the piece of view, the withe tension is 86 kips, which is less than the uh, reinforcing capacity of 222 kips. So we're okay, but this is another check that should be done when comparing both the outer and inner withes separately. Well, that's it. So thank you for your time, and other information is available at loshsoft.com and also by email. Thank you. Bye.